My name is Rachel, and I'm not a scientist. At least, I never thought I was. What you're about to find out is what I discovered when I got home one night before my parents. When you have a problem, your brain naturally tries to solve it by a mental and physical process that turns out to be scientific reasoning, hypothesis testing, or, when you apply a few rules, the scientific method.
The scientific method goes like this. 1. You make an observation.
2. You create a question about what you observed.
3. You develop a hypothesis consistent with your observation.
4. Use the hypothesis to make a prediction.
5. Test that prediction with experiments or further observations.
6. Analyze the results of the experiments or observations.
7. Make a decision to accept or reject the hypothesis.
8. If necessary, go back to step 3, create a new hypothesis, and repeat.
And 9. After testing thoroughly, formulate a theory.
When I'm the first one home, I always seem to have a problem finding the light. Here's what my brain does when I end up standing in the dark. This is my situation. Or if I were outside looking in, my observation. I come home at night, bumble around in the dark, find the lamp, turn the switch on, and no light. And here I stand in the dark. So the first question, of course, is the power out? My hypothesis. The power is out. Let's see. I predict that if power is out, then the lights are out at all the houses in the neighborhood. I'll experiment again and test the light. I switch it off, on, and still no light. Next, check for lights around the neighborhood. Analysis. If I see light in the neighborhood, then I must reject the hypothesis that the power is out. If I see no other lights, my prediction is true, and my assumption that the power is out is true. Since I see streetlights and lights in the windows around the neighborhood, I decide to reject the hypothesis that the power is out. But I'm still in the dark. What next? The question is the light bulb burnt out? My new hypothesis. The light bulb is burnt out. If the new hypothesis is true, then I predict the light will come on when I install a new bulb. I'll get a new bulb and install it. I put in the new bulb, and it lights. Analysis. The original bulb would not light, but the new one does. I can't reject the burnt-out bulb hypothesis, but I have no proof that the old bulb is burnt out. Another prediction. If the burnt-out hypothesis is true, then the broken filament in the bulb will rattle when I shake it. To test my prediction, I shake the old bulb. No rattling. My analysis leads to the decision to reject the hypothesis that the bulb is burnt out. How confusing. I guess more testing is called for. Maybe the old bulb was loose in the socket. Another hypothesis. The bulb was loose. Let's make a new prediction. If the hypothesis is true, then the old bulb will light when I reinstall it. To test the prediction, I tighten the old bulb. Now it lights. Analysis. I can't be sure that the bulb was loose. I decide I can't reject the hypothesis of a loose bulb because past events cannot be tested. I have no proof. The evidence here supports my theory that the bulb was loose in its socket. In science, a theory is an idea that is tested thoroughly. I mean really thoroughly. In fact, it's tested so thoroughly that it cannot be rejected.
Oops, I did it again. This is the second time this week I knocked my toast on the floor. My name is Khalid. I'm not a scientist, but I sometimes sort of think like one. That's what I learned in science class. You see, when scientists investigate things that they're curious about, they use a step-by-step approach called the scientific method. It gets them reliable answers. Without realizing it, I sort of explore stuff that I'm curious about in a similar way. Take my curiosity about jelly toast sliding off the counter and landing on the floor. It seems to always land jelly side down. I wonder if that always happens. Let's find out by starting with the question. Does toast sliding off the kitchen counter usually land jelly side down? Hypothesis. The toast usually lands jelly side down. So my prediction is, if I slide the toast off the counter, then would it land jelly side down? To test the prediction, I will slowly push 10 separate slices of jelly toast with equal amounts of jelly past the edge of a 36-inch high platform and count how they land. Analyzing the results, 9 out of 10 drops from a 36-inch high platform land jelly side down. This leads to my decision that from a 36-inch high platform, the toast will land jelly side down about 90% of the time. The hypothesis holds. I wonder what I could change to get the toast to land jelly side up. If the platform were higher, what would happen? This means changing one of the controls, like the height, into an independent variable. The question is, does sliding toast off a platform higher than 36 inches result in the toast landing jelly side down? So the hypothesis becomes, regardless of the height from which the toast falls, it usually lands jelly side down. If I slide the toast off a higher platform, I predict it will usually land jelly side down. To test this, I will slowly push 10 separate slices of toast from platforms at different heights and count the results. Each slice will have an equal amount of jelly. Let's analyze the results. The toast landed jelly side down for 3 out of 10 drops from 44 inches. 7 landed jelly side up. I decide that from a 44-inch height, the toast usually lands jelly side up. So the hypothesis that the toast usually lands jelly side down is rejected. Here's my scientific theory of jelly toast. If toast is pushed off a platform of 36 inches, it's most likely to land jelly side down. From 44 inches, it's most likely to land jelly side up. As I push the toast off the platform, it starts to rotate. So the higher the toast is, the most likely it is to land jelly side up. I wonder what else I can experiment with.
Let's summarize what we've just seen. When we look at the world, we notice patterns, correlations, and the cause and effect of events all around us. The scientific method is an orderly process for discovering the truth about the world we live in.
1. You make an observation.
2. You create a question about what you observed.
3. You develop a hypothesis consistent with your observation.
4. Use the hypothesis to make a prediction.
5. Test that prediction with experiments or further observations.
6. Analyze the results of the experiments or observations.
7. Make a decision to accept or reject the hypothesis.
8. If necessary, go back to step 3, create a new hypothesis, and repeat.
And 9. After testing thoroughly, formulate a theory.
Scientists consider a hypothesis a tentative theory that has not yet been tested.
They test it to see if it holds water and check it against available data. If the hypothesis holds, scientists declare the theory.
In everyday talk, a theory is generally a vague or fuzzy sort of fact.
To a scientist, a theory is a conceptual framework that explains existing facts and predicts new ones.
Take the sunrise. It occurs every day.
This is a fact explained by the theory that the Earth is round and it revolves around the sun while spinning on its axis.
The theory also explains other facts like seasons and the phases of the moon.
It allows you to make predictions about what will happen tomorrow when the sun comes up.
When can you use the scientific method? You can use it to analyze events that you can observe, that can be reproduced, and that are measurable.
People developing new products will use the scientific method to find out how well it works. Here's an example.
Let's say that you're developing a flea repellent for dogs called Flea made with natural organic substances. You want to make sure that it eliminates fleas before taking it to the marketplace.
So you assemble a team of scientists who will test it. Here's what they do using the scientific method.
The question in this investigation is, Does the new flea repellent actually eliminate fleas? Our hypothesis is A, new flea repellent causes B, flea elimination in C, dogs, or A causes B in C.
To test the product, your research team selects 200 dogs from various breeds that have fleas. They randomly divide the dogs into two subgroups of 100 and isolate them from one another into separate but identical environments.
The new flea repellent goes on the back of the necks of dogs in Group 1, but not Group 2. After 1 week, the researchers examine each dog for fleas and record the findings. If the results show that the dogs in Group 1 are primarily free of fleas, and that Group 2 continues to carry fleas, then the conclusion indicates a definite link between the repellent and the elimination of fleas. The new Flea Away product works, and off to market it goes.
Here are the steps of this process. The experiment begins with the hypothesis that A causes B in subjects of type C. The new flea repellent A eliminates fleas B and dogs C. This is called a causal relationship.
Group 1, the dogs who received the new flea repellent, is called the experimental group. The dogs that did not receive the repellent, those in Group 2, are known as the control group. The control group provides a benchmark for judging whether or not the flea repellent affects the experimental group.
The flea repellent A becomes the independent variable placed on the experimental group only. After an appropriate period of time, in this case 1 week, if only the experimental group has B, no fleas, the scientists conclude the hypothesis is correct. A causes B and C's. If fleas are not eliminated in either group or no B, then the hypothesis is wrong. A does not cause B and C's.
Now, we know what you're thinking. It never happens that way in real life. And you're right. This is an ideal example that ignores some of the real-world problems that scientists deal with every day. Usually, scientists don't see an all-or-nothing result because of the many variables that enter into an experiment.
The scientific method is a thinking process based on human curiosity. We are constantly questioning our quick-to-notice patterns, correlation, cause and effect situations that happen around us.
The scientific method. It's a process that follows this step-by-step procedure. 1. Make an observation. 2. Turn it into a question. 3. Develop a hypothesis. 4. Make a prediction. 5. Develop an experiment. 6. Analyze the results. 7. Make a decision. 8. Repeat the process if necessary. And then 9. State your theory. It's a process that leads us to a better understanding of our world and ourselves.